has multiple cores, and I'm pretty sure the oldest laptop here has at least 4 cores. That doesn't mean like you can run games at high settings, like Hogwarts, which just hogs memory and CPU. But like, what are you going to do with all those cores? At least you can put it to use for parallel programming. And today we'll see exactly how to do that. So most of the problems in astronomy, especially observational and big data astronomy, are embarrassingly parallel. We say it's embarrassing parallel because like none of the processes depend on each other. You could just run hundreds of them, and they wouldn't push out an error until you did a coding error. Until and unless it's a file mismatch error or something like that, there's no interdependence among them, and you could keep batch files running like that for like hours. So the main problem is it's tricky. Parallelization adds a lot of complexity, and you don't really want that until you know what you're doing, and until and unless your package or your code desperately needs to be faster and more robust. Until and unless that, you don't use parallel programming. But it's good to know. So we'll start learning about that. So this is what I said by embarrassingly parallel. So I just set up a dummy code. This is to find the brightest point in an image. Let's say it's a fits image. So I treat 2D arrays, like a bunch of 2D arrays as images, and then I run through 10 of them, and all of them have a similar size of 100 by 100, and then uh, I create a pool. A pool is, we'll see later, it's a multi-processing task where you spawn multiple workers. So it's like n number of workers doing the same thing, and trying to speed up the process or trying to run the same program again and again. So I do this and try to find the result, that is, find the brightest point in the image. And none of the images depend on each other, of course. It's fits files. All of them are interdependent. You run the program on these images and you're done. And yeah, you can get the results like these, and you can get thousands of them without having to do anything more than add 2 lines of code through multiprocessing module. And like I was talking previously, all of these cores, the multiple cores, are going to waste because um, like when you program, you're just using all of it at once, and it doesn't intelligently distribute your work, or you're not using your PC to its full capacity. So we'll see how to do that. GPU is a bit of out of scope for this class, but why? Uh, because of this. Like in today's world, parallel programming is mainly important because of workstations, uh, uh, HPCs. They are high performance computing and supercomputers. But for our case, we'll see how to use parallel programming in a package, or if your package even needs that. And because when you run on these supercomputers, you're running for yourself. You're just uploading the code to the headless server and letting it run for like days or weeks. But the final result is still worked on by you. So you know what you put in, you know what it will spew out. But when you are publishing a package, it's not just for you, but it's a whole bunch of people who will be looking forward for different functionalities and facilities in the package. So they don't know how to use it, and you should value their time. So if it's a very time consuming process, then you should think of adding parallel programming. Sure, I can learn about CPU, GPU, and multiprocessing modules, but like I said, most of the things can just be um, done by running the program multiple times or running multiple instances of those programs. So the 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 main point is don't add complexity to the code. And yeah, like I said, this might sound very unsophisticated, but it is sometimes the not sometimes, most of the times it is the smart choice. There are many options to do that, like GNU parallel, or you can create a master Python script. Master Python script takes another script in is like a main script that has calls to another script that is your main processing script or what gives you results. So you can, in your master script, create multiprocessing workers and then push it to the result. Yeah, the processing script, and then it will just run like the example I showed you before. And one more main thing while implementing parallel programming is checking resource usage, because debugging is hard. Just like we earlier noticed today, debugging is hard. Imagine debugging one code. Imagine now debugging 10 different sets of code with different sets of problems or conflicts. So the best way to do that is use, let's suppose I used 10 images in that example, but you for production level code, you're going to insert like hundreds of thousand images. You don't want to test on hundreds of thousand images. You can test on 10 images. If it throws out an error, you know where the error is, and you're not sitting there for hours trying to see, oh, when can I catch the error. So that's the first point. Use minimal number of parameters and minimal number of test cases. And the other is check system monitor or task manager when using this, because when you process multiple worker calls, let's say you process 10 worker calls or you issue 10 processes, and one or two of them might be lagging behind, the rest of them are already done with the process, but one or two of them are still lagging behind, and that can slow down the whole process. So you're not getting your optimal acceleration or increase in productivity that you want through parallel programming. So once you look at that, you can see which process or which worker is non-functioning, and you can see what error that worker is producing. We'll talk about it in the end of the module. So here's another example. I created a matrix of 5000 by 2000, a 2D array, and I'm trying to divide that divide that matrix using the index parameter. So what I mean by index is just I divide the matrix into 10 parts and I use 1 to 10 to denote that this is the first chunk, the second chunk, third chunk. So I divide the matrix into 10 chunks, and then I loop through all of those index numbers and use the multiprocessing libraries process module. So when I use that, I have to give it a target. Our target is the matrix loop here that we want to calculate. And then the arguments are the matrix I created, the first thing, and then the index. That's through the for loop. So as you can see, it tells you when the process completed and it tells you the value. The two most important things in when implementing multiprocessing is p dot start. and p.join. Join. What p.join join is, you are saying that you created a process list, like you're creating an array of the number of processes and the name of the process that you have, and you're telling them to start after this loop, and then at the end you're telling them to join and give you the result at the end. So we'll talk about pools now. In the previous example, like we literally just take this part, the matrix loop definition, we give it a separate we give it a separate block this time, and we'll return the values. Now, last time I just manually separated the chunks, or manually divided the matrix into chunks, and then I looped through it manually. But you don't want to do that. There's a better way to automate that, and that's through pools. So what pool does is spawn n number of processes that, like, you give it calls, number of processes is given by you, and here we choose process equals to 8. So we have 8 different processes that are ready to do the work in parallel, and then we apply the same loop again using apply async. So pool has a special thing called apply async. There's another thing called pool.apply, but the two versions are async and apply. So async does asynchronous parallelization. You'll look at the results and figure out why it's called asynchronous. So it created jobs, and then it tells you when the job is complete. It tells you its result. Job 1 is complete. It tells you the result. And then you see job 2 and 3 are both completed together, and it tells you the result later. And as soon as a job is completed, it tells you the results. But when you use synchronous parallelization, you get the results at the end. That's because it doesn't end. So we started the processing through p.start. We ended through p.join in the multiprocessing module. Here we use pool.close and pool.join. So pool.close tells you when to end the process, and pool.join then combines all of the results from the process and tells you the results at the same time. So this is synchronous. You can say that, you can think of it as everything and all of the processes working in tandem. Asynchronous is as soon as the results out, it tells you the results. That's it. Right.
Regarding the time, when you are using the second example, is it like the time of each of the job or combining everything? Because when you're doing in synchronize, we are expecting that the time will be shorter than doing in parallel or something. Is the time consuming shorter or the same?
So
Repeat the question.
Okay. Okay. So someone asked me that is asynchronous faster or is synchronous parallelization faster? Because if you think synchronous parallelization means that everyone works in tandem, so it should be done earlier. But the problem is most of the times it's equal, and in cases there's like you already have many processes, or you already, let's just say you have many tabs open, and your PC is not at full your PC is almost at full capacity. In those cases, then synchronous parallelization will actually be slower than async, because some of the processes can take time more than the others to complete. So in that case, all of them will wait for all of the process to be complete, and only then will the result be displayed. So async is fast. It gives you your result as soon as it's done with the result. But synchronous, everyone has to wait, and you'll get your result at the end. So in both have use cases. So synchronous is highly recommended when you have multiple variables that are dependent on each other, and let's suppose you have a matrix and you have a numpy array that converts the matrix into a 1D array. In that case, you want it to be synchronous because uh, let's suppose this like the conversion of 2D to 1D array takes precedence than the matrix multiplication, then it will give you an error because there's nothing for the conversion to be done on. We'll talk about two main libraries, not libraries, but protocols. They are protocols, a set of rules and a set of architectures that were made mainly for parallel programming. They are OpenMP and MPI, message passing interface. You can look at this later. It's pretty informative, but we'll skip to this. This image is enough to know what's the main difference between MPI and OpenMP is. Sorry. So in OpenMP, you have a block. Let's call this a block. Let's call this a whole. Let's call this whole thing a block. So a block may have any number of cores. Let's say 2, 4, 6, any number of cores. But all of those cores have a shared memory. That is huge. And all of these cores use the same shared memory and same data from this shared memory to work upon. But in MPI, you have uh, 4 blocks. So a CPU core plus its own memory is a block. Instead, in OpenMP, n number of cores plus their shared memory is called a block. So in MPI, each core can only access its own memory, and everything has to be computed through the core or the processor, and then it's passed on to the next core or communicated in between all the cores. But everything is done here first and then communicated. But in this case, in OpenMP's case, they all communicate at the same time because same memory. OpenMP was primarily made for Fortran, C, C++, and we won't be talking much about it because Python can't do OpenMP. Because there's a thing called global interpreter lock. That means Python can only talk to one thread at a time. So OpenMP can actually, the main idea of OpenMP is using multiple processes, but this can't, like Python can't do that. I'll just leave these if you are interested in implementing in C++. And now let's move on to some examples. So I'll be building a Monte Carlo NC solver that basically models the radioactive decay of lithium, and we'll use this both in serial. Serial is your normal task, uh, normal task procedure. So it does one after the other. It's continuous, while parallel is like doing the same process at the same time for a number of times. So I have already coded it out, and it's pretty. Uh, it uses the Metropolis algorithm, and I'll give you guys 2 minutes to look through it. But the main thing, yeah, that you have to look through is just the Metropolis block. Just understand what the variables are and what I have initialized them with. Then we'll move on. All right, let's move ahead. So the basic setup is we are calculating uh, the number of particles left after uh, the half-life or like the radioactive decay of lithium. So we have for my case, I have 100,000 particles, but if your laptop is a bit old, you should reduce it to 1,000 or maybe 10,000. And it has a half-life of 0.8387, and we are running it for 1 second with a time step of 0.001 seconds. Now, I'm using serial decay, so I'll run the process 100 times one after the other. So you can see it tracks like after 0.83 seconds, there's only 50,000 lithium ions left. So this shows that like our algorithm is pretty sound. So in serial decay, it's literally a simple for loop. In the Metropolis decay algorithm, I output the time it takes, uh, the number of decayed particles and the number of undecayed particles. We are using the Metropolis decay to store results in these time points, undecayed particles and decayed particles. And then we're just using uh, the time points and the undecayed particles to plot it. That's it. A simple for loop. Okay, I'm gonna reduce my number. Since it's collab, I'm only running 10 such processes. That's quick. Okay, I'm back to 100. Okay, so for 100 simulations to be run back to back, it took the serial decay 10 seconds. So it took the for loop 10 seconds to process through it. Now let's look at parallel decay. And I did one, you guys do one. Go ahead and fill in the blanks. All right, let's see how we can complete this problem. I told you it's literally the same as the matrix problem. All you have to do is use the multiprocessing module, issue worker calls, and you already have a definition for the worker function. You just have to complete it. So all that's different in this worker function is I initiate every worker with a random seed. That's to introduce randomness so that our results are different each time. So I create a tuple where I store my uh, decay algorithms results. So I use the same things that I used in the uh, worker parameter, the function parameter. And then I take these results and push it into a dictionary just for later use because we will be needing them and you'll see why. So this completes our worker function. Now the number of processes is the number of CPUs everyone has, so it will be different for everybody. And then we'll use the multiprocessing modules manager function to create a parallel simulation manager. And since I didn't tell you about this previously, so I did set it up already. Now we'll use the time library to start to start the timer here. And now we issue the processes function where we push in all of that metropolis decay calls with the number of loops. Previously, we gave the matrix loop as a target. Here, we give metropolis decay as the target. Should do it. Now, like I told you, the two main things to remember about the MP module is starting and joining the processes. So for all the different processes in our processes module, we'll be starting it. For P in processes, P dot start, and similarly for P in processes, P dot join. And you can't do this together because it has to start, it has to calculate everything, and then it has to be joined together. Or else, if you start and join together at the same time, it's basically serial processing. So it's gonna run like a for loop. And then And after everything's done, we'll end the timer here. Okay, what? Hmm. And then use the plotting. Okay, how much? Wow. Well, I guess Collab doesn't understand what parallel is because my laptop serial runtime for 100 simulation of 100K particles was 28 seconds. And
Yeah, maybe the settings are different in Collab.
yeah, it doesn't know how to run MPI run either. That's why I didn't want to use
Definitely
Collab.
MPI doesn't, yeah. Your question?
Yeah, I guess I was wondering with the implementation of like putting the results of each run into the output dictionary at index seed, do you have to worry at all about like if because when you generate the random seeds, do you ever run into like multiple
Duplication?
instances having the same seed and
Oh, yeah.
overwriting?
Most of the times not, but there are cases it can have the same seed. But rand end, if for that specific function, I don't think it will give you the same seed.
Oh, okay.
Yeah, and we are using rand end, so it has to be discrete integral numbers.
I think there's a like with or without replacement keyword that you can set to, but I don't.
Okay, if I had a camera, I would show you guys, but you're just gonna have to trust me that my parallel runtime was 4.47 seconds and my serial runtime was 27.8 seconds.
He's telling the truth.
Okay, now moving on to MPI. But like I told you, OpenMPI doesn't run on Python, but we saw two examples of multiprocessing module. Why did I say OpenMP doesn't run on Python and still went ahead to tell you something about it? That's because even though OpenMP is not feasible on Python because of the global interpreter lock, but the Python, that is C plus Python backend in Python, can skip it, can get through it. So multiprocessing module is basically OpenMP applied through Python in Python. So if you want the shared storage feature of OpenMP, you can use multiprocessing. But for MPI, you have OpenMPI, not to be confused with OpenMP. I don't know if they don't know how to figure out different words, but they all sound the same. So you can use OpenMPI's MPI for Pi module to implement MPI in Python. And I've explained before, like what's the main difference between MPI and OpenMP. That depends on your use cases. Like if you want something calculated and then uh, moved forward or uh, processed to the other function, or if you want both of the functions to process together, that totally depends on your use case. But MPI originally in C++ was a pain in the butt, because in OpenMP you could just like when you implement OpenMP in C++, it literally just looks like comments and it's small. But with MPI you have to, like, it has its own syntax. Good for you, you're using Python, you don't have to worry about that. So we have another example. Do you guys have the repo? I would like you to open nbody.py. Open the nbody.py file and yeah. So the three main things of OpenMPI apply here too. Like you have to start the processing, you have to start the parallel processing by broadcasting the data that you have. So in MPI, you initialize the program with just one major or one parent worker. But then that parent worker has all the data that is then broadcasted to all the child processes. So we use the broadcast function. Where is it? Yeah. So right after the MPI run code block, do not run it yet. Right after the MPI code run block, you can see that the initialization routine is only on the rank 0, that is the main MPI process. How do we share data with other MPI processes? We use broadcast. Communication.bcast is com broadcast. And you always start with mpi.com_world. That is saying that like the whole program is communicable, like you can communicate across the whole program. So it's setting up its own communication world. And then let's say like each core works on its own thing, but like how do you split the work, just like we did in multiprocessing? Like how do you create chunks of the whole process so that you can split it? Here you use com.getSize and com.getRank. GetSize tells you the total number of processors that you have, same as os.cpu count in multiprocessing. It tells you the total number of processors that you have. And then getRank is just like each processor gets assigned a number, and it's 0 to number of processors that you have. So you just use the rank or the number to call or to specify what to do with that specific processor. And then once we have broadcast all the data, then each processor has its own chunk of data calculated, but then we need all of that data to be known to all of the cores. So we use again the broadcast and double calls to share results among all the processors. All gathers all of the results, and then MPI double is just the data format. Now there's a specific I don't know if this will run or not, but
Probably not in the collab.
yeah, it needs the sudo access.
Yeah. It's all good. Why don't you describe what it would have done?
Okay, for the in-person people, I'll just uh, at least the two in-person people sitting there. So what you see here in is I just used the explanation mark to say that this has to be run in Bash terminal, not Python. So MPI run is accessed through MPI for Py library, and the dash n flag and followed by the number tells you the number of processors it's going to use or you want it to use, and then since it was basically meant to be used in C++, now you have to give it the name uh, of the programming language, Python, and then nbody.py. So what happens here is it uses flag n1 uses only one processor, flag n4 uses 4 parallel processors, 8 uses 8 parallel processors, but my laptop has 8 processors, that's it. But there is an option for me to go beyond that. The results may or may not be better, but there's a at least they gave you an ability to go beyond that. So you use the oversubscribe flag and go beyond the number of processors that you have to get a marginally better result. So in most cases, from when you jump from 1 to 4, it will give you almost a 4x speed up. So it's a linear speed up with the number of processors that you implement. But when you oversubscribe, it means that I still have 8 processors, but I'm trying to jam 12 MPI processors in 8 processors. So that means 4 of the MPI processors have to be doubled up on some processors, or they will be sharing uh, like 8 of the processors that I have. So it's gonna be chaotic, and your results are gonna be suboptimal, and it's better to not oversubscribe. The same thing applies in OpenMP2. Using MP multiprocessing module, you can access more workers than you have the physical capability to do so. But again, the results are not going to be optimal. So
Will I switch over relatively soon too?
yeah, I'll be done in 5 minutes.
Sounds good.
So we saw debugging earlier today. There is a way to use parallel debugging, but it's again a pain in the ass because you don't want to do that. It literally opens terminals. It literally opens windows that are 80 by 60 pixels in size, and you can't see shit. You can't maximize it, and it's basically just spawning n number of terminals, and each terminal has its own process. So if you have an error in your code, one of them will get stuck somewhere and then tell all the other process to stop there. So in this way, you're not sitting there for hours trying to see if it's going to run, or you're not wasting your precious GPU time or CPU time. So if one of the debuggers finds a problem, it will tell all of them to stop. If it's working, it will tell all of them to go ahead and give you the results. Everything else is optional. We'll come back to this. Give me a minute. Yeah, this is Jason's meme, not mine. I can't do this yet. So, do you really need parallelism? I don't think so. For your package at this point, no. If you're going to do like a lot of coding in the future, definitely. But for now, I just wanted to tell you that there is a provision for you to use parallel programming, but don't, don't. This is gonna be you guys tomorrow. I know. Okay, and now we have an activity for after the class. That's image processing. You'll be creating some fake data in the format of fetch files, and you'll run it both in serial and in parallel using the multiprocessing module, and report the results on Piazza. I'll be posting a question soon.